Hello there, this is Nigel Goldenfeld at the University of Illinois at Urbana-Champaign, and this is a recording of the speech I was going to give at the Kadanoff Prize Symposium at the APS March meeting, which unfortunately was cancelled due to the coronavirus. So let me begin by saying how grateful I am to APS for bestowing this magnificent award upon me. Elsewhere, I have given a short 2-minute acceptance speech with various thank yous and acknowledgements, and so I will let you find that on this YouTube channel, and I will move on to the scientific content of my talk. So the topic of my talk is how one can understand complex systems, remarkably complex systems, with the relatively simple modeling ideas, all based on renormalization group type of concepts. And this is something that resonates a lot with this session and this award, because it arose and was reflected in a science article that Leo and I wrote in 1999, trying to talk about how one can model complex systems and what one can learn, what general conclusions one can learn about complex systems. Are there general patterns that we can see? But what I want to talk about is how one can turn this round and not so much think about simple lessons from complexity, but how we can learn complex lessons from simplicity, from simple modeling. Now, let me just say a few words about the interactions with Leo Kadanoff, since it is appropriate for this session. So Leo was, of course, at the University of Chicago at the time that I joined Illinois at 1985, during the glory days of pattern formation. And we collaborated extensively with his group there, Albert Livschabert and others, studying turbulence and pattern formation, Healy-Shaw cells and things like this. Here's the only picture I have of us together. This was at a colloquium in Urbana, and on the right you can also see my colleague Eduardo Fradkin, who was also a close colleague of Leo's. Now, Leo and I used to go back and forth many times. Let me just tell you an anecdote that shed some light on Leo's character. I was visiting Leo sometime in the 1990s when he was the director of the Materials Research Lab, I think. And he had to introduce a speaker who was in a field that wasn't close to his. Maybe it was chemistry or geology. So he gets up there and astounded us by proclaiming the bold lie that he had followed the speaker's career very closely, which of course usually means that the person has followed the science that that person has done, and which seemed surprising given the topic. But as Leo made the traditional recitation of the visitor's biography, namely, this was the university where this person did their PhD, where they did their postdoc, first faculty position, and so on, it became clear that this person had been at the same universities as Leo, but moving from them a year or so before Leo made his own career moves. In other words, it was indeed completely true. Leo had followed his career closely. Now, when I moved to Illinois, in some sense following Leo's career, I was talking with Leo, and he said, well, congratulations on the move. Illinois is a great place to start a career. And so that in Leo's speech, that means, but not necessarily a good place to end a career. And so I asked him, well, why did you leave? And he said, well, basically, there was nothing to do on the weekends except go and visit the pig farm. That's not true now, for sure. It may have been true in the 1960s, I don't know. So anyway, Leo used to say often that he had done his best work at Urbana, and I think most people would agree that that was true. Let's just quickly go over that because it's germane to what I'm going to talk about. So this is a review article that he wrote, a very detailed review of experimental data near critical points. Some of the names here you'll recognize as they became distinguished scientists in their own right. And at that time, they were students in a special topics class that Leo taught, and they analyzed the data, and then they all were co-authors on the reviews of modern physics paper. What they were doing then was collecting data and showed strong evidence for universality. They tested the various scaling laws that had been proposed at the time, and they looked at the experimental data and performed a data collapse, which, as you may remember, was in fact the predictions that Leo had made in this famous paper in 1966, based on Widham's conjecture at around the same time about the homogeneity of the free energy. And Leo famously showed by his block spin construction how one could obtain these scaling laws and data collapses subject to various assumptions, which were later indeed clarified by the renormalization group by Ken Wilson. Now, one of the great successes of theoretical physics is, in fact, this graph here, shown from a paper by Gene Stanley. So this shows you the magnetization of a bunch of magnets, magnetic materials, which ostensibly should depend on two variables, the external magnetic field and the temperature T. But when plotted in the way that theory predicts, you see all these data collapse onto one universal curve, the same curve, and in fact that curve is the same one that obscures, that is the same curve that is this solid line here obscured by the data, which comes from a renormalization group calculation of the 3D Heisenberg model. And so this is a great success. It shows universality, that regardless of the material, they all fall onto the same universal scaling function. This is remarkable because you might say, well, this Heisenberg model is makes wonderful predictions in agreement with experiment, but actually it's not really a model. It's more a model of a model of a model of a model of a model. Why? Because you start off at the lowest level of description with quantum chemistry, you then derive the electronic structure, from that you obtain a quantum Heisenberg model and a classical Heisenberg model, eventually Landau theory, and then the renormalization group predictions. But the point is that none of these steps in going from here to here to here to here is systematic or justifiable a priori. They're justifiable at the end once one understands the renormalization group picture of universality. But it's a remarkable and surprising fact that one can make a series of non-systematic approximations, brutal approximations if one will, and yet get precise agreement with the most accurate experiments and theoretical calculations. Now, after leaving Urbana, Leo moved to the Brown University, where he pursued urban studies. And what he was interested in there was trying to understand computer models of urban change, which could then be used to prescribe social policy. Now, early experiments on this had been done by J. Forrester at MIT, and Leo was not happy with the policy that resulted, and so he set out to do the same thing using the same modeling tools to get results that were more to his liking, and he succeeded in doing that. And in fact, he discovered that he could accurately record the prejudices and points of view that he had. And so after a while, he says, the point we had made began to sink in. If these models really represented little more than we could say in words, then why not leave out the computer? So the point is that this sort of computer model seemed to Leo to be a rather pointless endeavor, and for this reason and others, he moved away from urban studies, moved to the University of Chicago, and resumed work on critical phenomena. All of this is described in a nice book of his, From Order to Chaos, in the early 1990s. Now, the moral of this story is that there are two ways to model nature. One, you might call excessive realism. Everything is computed as accurately as possible with many levels of description and fitting parameters. The alternative is minimal models. Everything is computed as sloppily as possible with as few levels of description as possible and as few fitting parameters as possible, taking this model of a model of a model of a model of a model philosophy seriously just make brutal approximations and hope that there is some sort of universality going on. In other words, under excessive realism, what one can do is compute to get numerical information, precise numbers, many decimal places, that verbal arguments on their own could not address and achieve. On the other hand, what can one get from these brutally simplified minimal models? Well, one can find the phase diagram. One can find emergent phenomena. Emergent meaning an outcome of the dynamics that is not mandatory and is usually collective. As an example, you could start with a Hamiltonian of a fluid. It's the same as the Hamiltonian of a solid, but only for low temperatures is there a non-zero shear modulus. In other words, the springs that we put in to connect the atoms in simple solid-state physics models of a crystal, those springs are actually emergent. Now, why is theoretical physics so successful then? Why is it that we can achieve accuracy of predictions compared with experiment to many decimal places? Well, it's not because we're smarter or better in our science than other disciplines. It's because we only ask simple questions, and think for a second before where I'm going to go on with this, we ask questions at the top level of description. And that means we don't ask questions which depend on the details at lower levels of description. We've learnt how to do this. We don't necessarily know a priori what are the right questions, but we have got some experience and intuition about this. So let me now give you some examples of universality in minimal models in practice. So here are three different pictures, representations, if you will, of polymer molecules. The one on the left is what a chemist might use, and it is useful for understanding chemical bonding and reactions and so on and so forth. Here is a model of biopolymers where one might want to understand the elasticity, large-scale motions, protein folding, and so on and so forth. And on the right here is how a theoretical physicist views a polymer, basically spaghetti. Basically just forget about the atoms, forget about any atomic detail, just ask what are the properties of matter that arise from the fact that the fundamental ingredients are long stringy objects rather than round blobby objects. And the answer is, well, one can compute the thermodynamics, the light scattering, the rheology, as my PhD advisor Sam Edwards did with Masao Doi, and this works very well. So as an example, consider the question, how big is a polymer? What is the end-to-end distance, the mean square end-to-end distance? Well, the chemist would say, well, that's easy. We can model the bond angles, the energy barriers to the isomeric rotational states. We can understand the interactions with the solvent molecules. We can sample over long times or many independent conformations, do molecular dynamics, and we can predict R in angstroms. The theoretical physicist says, no, we don't need to do that at all. A polymer is just a random walk of n steps, each of length L. Einstein taught us that the R squared goes like little l times big L, and so therefore we know that R should scale as L to the power 0.5. Now that's completely wrong, because a polymer in solution cannot cross itself. Two atoms cannot occupy the same point in space, and so we expect the chain to swell, and in fact the normalization group arguments tell you that R actually scales as capital L, the total length of the polymer, to the power 0.588, etc., etc. This scaling is universal, and it's asymptotic for large chains. It doesn't predict R in angstroms, but if you know for one value of L what R is, then you know it for all values, at least for long chains. And so each of these descriptions have their own virtues and uses. Here's another one that is dear to my heart. This is from my colleague Yoshi Ono and Takao Ota. Yoshi and Takao pioneered, along with others, the description of polymers in solution using real space renormalization group theory methods. And here is an example: the osmotic pressure as a function of concentration. The data are plotted, I should say, in a way predicted by the theory, and the solid line is the epsilon expansion calculation, and the dots are data from Wiltzius et al., done after the theory was done, and the data, again, fall onto a universal curve with no adjustable parameters and no material-specific parameters. So this is an extension then of what we saw with the Widom scaling collapse for the magnetization of our magnet. So what we've learned is that the spaghetti model of a polymer is an example of a minimal model. It's good for answering certain questions, but lousy at answering others. And in fact, I would argue that successful scientific predictions are always the results of minimal models, because you cannot include every detail in a model. Usually, in physics, there's only a few details are important, and so there's a separation of energy scales. And physics, in that sense, is easy. Chemistry, on the other hand, for those sorts of questions, you absolutely need a lot of details, but at the atomic level. You don't need to worry about the radiative corrections to the mass of the top quark in chemistry. So they're also using minimal models, but at a different level of description. In a field like economics or sociology, perhaps, every detail may matter. We don't know. There's no obvious separation of scales, and those problems are extremely challenging and perhaps not suitable for this type of description. Now, at the beginning of my career, and at the time when I first came to Illinois, we were interested in understanding whether there was universality in pattern formation. So here is a picture of the microstructure of a metal. You can see a bunch of interlocked dendrites shown here. And we don't have a scale bar here, but we know that what the scale might be. The important thing is the pattern and not the scale. Now, if you want to actually build a material to make something strong, to design an airplane engine turbine, for example, of course you need to know that, and that can be measured. But one wants to understand the actual structures, that happened, their emergent properties. Then one needs to do this sort of modeling. And we did this sort of modeling back in the late 1980s and 1990s, looking at spinodal decomposition, phase separation of a binary alloy as you cool from a high temperature to a low temperature, get two coexisting equilibrium phases in equilibrium. But during the time dependence of that, what you see is a pattern that gradually coarsens, as I've shown here. And you can see if I expand part of this inset and expand it, you can see that they look statistically the same. So in other words, enlargement is the same as time evolution, showing you that the dynamics is in fact scale invariant in time. And we can test this with neutron scattering data. Here shown data from copper manganese alloy in this rather nice paper, where you can see the structure function as a function of wave number. The peak moves to smaller and smaller q as the domain sizes grow, and when collapsed according to the way theory predicts, you see a lovely data collapse for many times. One can do this computationally, turn it into a computational tool, because instead of solving the differential equation that one might use to describe these sorts of processes, say the Kahn-Hilliard equation, what one does is divide the system up into coarse-grained cells and write down an iterative map that tells you how the dynamics evolves, and just find a map that has the right fixed point structure describing the equilibrium phases. Then what one does is couple the cells by diffusion and implement the mass conservation law if you're looking at a conserved dynamics. The end result of that is shown here. This is an example of something we did with Paul Goldbart and Martin Zawitowski in the middle 90s. This is isotropic nematic transition, looking at the dynamics of topological defects. And you can see here that the pattern grows in time. These are experimental data from Nagaya et al. The original predictions that we did were actually done. This model is related to a different type of model, and an XY model, and we had done those calculations in the early 1990s. By 1995, they could test these predictions experimentally, and here is the results. This is the scaled correlation function from our paper in 1992. This is the scaled distance when the experiments are plotted in the way that the theory and simulation suggest. You can see that they agree very nicely. The black squares are the computer simulations, the dots and crosses and so on are the experimental data, and the solid line is an analytical theory done in a sort of 1/n type approximation a kind of mode coupling approximation by my former student Feng Liu and Jean Mazenko. So what we see from this is that even though these models are explicitly not grid converged, they're horrific from the point of view of traditional numerical analysis. Nevertheless, this minimal model captures the important features of the data. It shows you how one can see the data collapse of the correlation functions of the topological defects as a function of space and time. So what I've told you then is predictions rely on the existence of minimal models. Computational algorithms can model very simple processes that generated complicated space-time structures, and one can even make quantitative prediction of universal quantities, scaling functions, not just scaling power laws, in excellent agreement with experiment. So now I want to turn, for the end of this talk, I want to talk about some new results we've obtained looking at scaling laws in evolutionary biology. And this scaling law is in fact a topological scaling law, and I want to tell you something about that. So this is work done with Qi Xie and Jiru Liu, who was an undergraduate with me at Illinois, and Qi was a graduate student. So this is Carl Woese, one of my mentors in biology, in characteristic pose, sitting in his office at the University of Illinois, photographed and presented in the New York Times, Thursday, November the 3rd, 1977. Carl Woese was on the front page of the New York Times because he had mapped out for the first time the evolutionary history of life on Earth. At that time, he hadn't got all of it, he'd done some of it, but what he had done already showed that the structure of life was tripartite, that there were three domains of life: bacteria, eukaryotes, organisms which have cells with a nucleus like you and me, and archaea, things that look like bacteria, but are as evolutionarily distinct from them as you are. And there's you, and here's the archaea, and you can see that they have a completely different evolutionary history from the bacteria. So this was a big discovery. Now, when we look at these so-called phylogenetic trees, what we're looking at is at the edge, right now, we can see various organisms, plants, funguses, and so on and so forth. We can infer the evolutionary history by asking from the gene sequences of the 16S ribosomal RNA gene, or 18S, we can ask what must have been the evolutionary history in order to produce this structure today. And so we can infer internal nodes that tell us about the organisms that must have lived back in time. And that's what these phylogenetic trees show us. So the ancestor nodes are derived by comparing the relatedness of sequencing data of descendant species. And by now there's a very well understood systematic way to do this. So phylogenetic trees represent the world line or trace of the evolutionary process. And in a very real sense, they are the Feynman diagrams of evolution. And what I want to discuss now is what can we learn about the large-scale structure of evolution from these world lines. So here is a phylogenetic tree, obviously very complex. This is a real phylogenetic tree. It's self-similar. If I take this part of it and blow it up, you can't really tell the difference from the previous part. So how can we quantify that? And what I want to talk about is just one aspect of that, which is the topology of these phylogenetic trees. There's other things that one can talk about, but I don't have time to go into it here. So if we look at the topology, we see a branching structure like this with nodes and edges. And what we're going to define is the number of nodes of the subtree rooted at a given node I. So for example, choose this node. It has one subtree going down from it. This node here has two subtrees going down from it, plus itself, so that gives you the number 3. This one has itself plus two subtrees with nodes with values 3 and 3 respectively, by symmetry, added to it, and so its number is 7. So that's the subtree node number. The cumulative size, C, is defined as the cumulative sum of these subtrees. So here it's just 1, here it's 3, plus the sum of these two, which is 5, and here it is 7, plus the sum of these two, 5 and 5, and that gives you 17. Now the question is, how does C vary with A? And what happens is this. If the tree is completely balanced as shown here, then C actually scales linearly with a logarithmic correction, asymptotically. If, on the other hand, the tree is maximally unbalanced, as shown here, then it goes as the square. What do real phylogenetic trees do? Well, what real phylogenetic trees do is that the cumulative value scales with the node value as a to the 1.4. I don't know about this last decimal place, but certainly something around 1.4 plus or minus 0.1. And the question I want to understand is where does that come from? So what is the origin of this non-trivial power law, and what does it tell us about living systems? And what do power laws tell us about physical systems? Well, let's talk about what happens near a critical point. At Tc, if I look at the correlation function at Tc as a function of wave number, it scales as wave number to the power -2 plus an anomalous exponent eta. And you might say, okay, that's fine, I read it in textbooks, but wait a minute. If I do dimensional analysis, this correlation function has units of length squared. So how can it scale like this? Well, the answer is scale interference. The lattice spacing comes into this correlation function as a prefactor, also raised to the power eta, restoring dimensional analysis. And even though the correlation length has grown to close to infinity as you go closer to Tc, the lattice scale is of the order of angstroms. Nevertheless, the lattice spacing still enters in to the long wavelength correlation function. It's non-intuitive, and it means that the system remembers the small scale details, even if the correlation length has gone to infinity. And the fact that you get scale interference reflects what it does is it reflects the fact that a length scale that you wouldn't have thought would matter actually does matter. And this is in fact the origin of why you get anomalous exponents near critical points. So is there scale interference in evolution, and how could it arise? So here's the evolutionary process. The lengths down here actually reflect the numbers of mutations of base pairs in DNA. That's how they are quantified. So that's the evolutionary process. Now what happens at these nodes is an ecological process. It's ecological because a speciation event has occurred, but it's only occurred locally in space. And then gradually that speciation event has to go to fixation in the population. There have to be enough of them in order for them to be sampled and represented later. So these nodes represent ecological processes. And here is a beaver doing an ecological process that I think is a very important one, which is it chops down a tree. The tree then causes a river to dam up. That causes a big swamp or pond, and that opens up the way for new life forms to enter that environment and in fact to alter it. So this is a long time scale, and this is a short time scale. And when we draw a phylogenetic tree, we're setting the ecological time scale over the evolutionary time scale equal to 0. But as I just explained to you, the activities of the organisms in the ecosystem can change the environment and can change the population structure, and the population structure can then change the environment, and that in turn can change the evolutionary trajectory of the entire ecosystem. And so you have this process now quite well documented over the last 20 years of rapid evolution, or sometimes it's known as niche construction. So in niche construction, what you think about is this. O means the organisms and E means the environment. Traditionally, you might say the organisms undergo some dynamics in the background of an environment, and the environment just depends on itself. But now what we're saying is, if there is this feedback between the organisms and the environment itself depends on the organisms. And so that means the organisms can change the environment, and evolution becomes a collective phenomenon. In fact, we know this is true because that's how you breathe oxygen. So here's what happened. Sometime around 2.6 billion years ago, cyanobacteria produced oxygen as metabolic waste. That oxygen accumulated in the atmosphere. The anaerobic organisms died, and aerobic ones evolved, and that's how we have the biosphere now that we live in. Very high energy organisms that can use this rocket fuel of oxygen in order to do remarkable things that eukaryotic cells can do, but would previously have been impossible in the environment that existed before the great oxygenation event. So this feedback means that the timescale separation is not valid. Now, we think of particle interactions as Feynman diagrams, and in ecology, we can do that as well. For every ecological process, we can write down a diagram. For example, A is a predator and B is a prey. So when a predator meets a prey, it might eat it and then have enough energy to produce a baby predator. So your A plus B goes to 2A. This is a kind of chemical reaction process describing the interactions between organisms in an ecosystem. And we can represent it by this Feynman diagram, where the prey are the wiggly lines, the predators are the solid lines, and you see this diagram here is a predator meets a prey and produces two predators. Now this is not fanciful. This is actually mathematically true. So here, for example, are some of the diagrams of vertex renormalization in QCD. Here is the diagrams that represent population dynamics. So here I showed you, I said to you that phylogenetic trees are the Feynman diagrams of evolution, but this is really true. When one looks at the stochastic field theories generated by these ecological processes, one finds that one can compute the ways that predators and prey interact and produce space-time structures and patterns, and using the tools of quantum field theory. And our group and Uwe Teuber and other people have been very active in doing this. And I refer you to this wonderful paper by Uwe, which goes into this in great detail. It's a very nice introduction to the subject. So the idea then is that in niche construction, what we're looking at is niches, i.e. the position of a species in its ecosystem. The niche construction is the mutual interaction between a species and its ecosystem. And then the survival and diversification of a species depends on its niche, and that is an ecological process, and then that affects the evolution of the system. So we model that in a minimal way. The idea is take nodes in the phylogenetic tree and assign them three variables: the available niche, the speciation rate, and the extinction probability. The idea is fundamentally this: after there's been an extinction event, there's lots of open niches available for colonization, and so that will lead to an increase in speciation. And that certainly is observed in the fossil record. So we make a dynamical system that describes this. So this is the fluctuations in the number of available niches. That's a multiplicative process that tells you about inheritance. Speciation, well, the more niches there are, the more likely to speciate, and that's described by this here. But of course, the niche number must be positive. And if it's zero, if it's less than zero, then we're going to set it equal to some constant. Otherwise, it just depends in an increasing way on the number of niches. And finally, of course, there are extinction processes that bound the growth rate of the system, the number of species. This rule here has embedded in it some kind of non-analyticity, some kind of singularity. So watch that, because that's going to be where things go interesting. When we now calculate C as a function of A, increasing the width of the fluctuations of the niche number, what we find is that as that increases, the C as a function of A increases and gets close to this power law scaling with an anomalous dimension e to the 1.5. That's what we saw in the experimental data. And in fact, the other characteristics of clades in ecology are also captured as well. I don't have time to go into that. So are these really anomalous power law scalings? Well, yes, they are. Because of this singularity, once you reach that boundary, it's some kind of absorbing boundary. And the larger is the fluctuations in the niche number, the higher chance you have to reach the boundary, and so the more asymmetric are the trees. So we can test this by working out what should be the data collapse scaling following Leo's RG ideas. And you can see here our data scaled in the appropriate way, and we see a very nice data collapse. So what I've shown you is that the origin of these non-trivial power laws is niche construction, or at least that's a process that can give rise to them. There may be others, I don't know. And the interplay between ecological and evolutionary processes. But what do these things tell us about living systems? It tells us that evolution is more than just mutations, horizontal gene transfer, and so on and so forth. One must take into account the ecological dynamics that leads to genetic fixation, even on timescales of billions of years. Processes such as competition, predation, range expansion, metabolic cross-feeding, and so on and so forth. So what we've learned then from this model is that phylogenetic trees really are the Feynman diagrams of evolution. Topology of phylogenetic trees exhibits non-trivial scaling laws, and the origin is exactly the same as in phase transitions and in quantum field theory, scale interference. Scaling laws reflect the indelible footprint of short-time ecological processes on the long-time scale of evolution. Well, this is, I think, a remarkable and fascinating conclusion, and I'd like to think that this is one that that Leo would find amusing and interesting. So with that, I conclude.